Welcome to Spaceverse, your portal to cosmic adventures. What if a planet didn't orbit a star? Meet SIMP 0136, a mysterious, free-floating planetary mass object drifting through our galaxy, unbound by the gravity of any sun. Roughly 13 times the mass of Jupiter and located just 20 light-years away in the Milky Way, SIMP 0136 spins rapidly, completing a full rotation in just 2.4 hours. It's an astronomical oddity, part planet, part brown dwarf, and now it's helping scientists unravel the complex story of weather beyond our solar system. Until recently, astronomers thought SIMP 0136's strange variations in brightness were caused by thick clouds swirling through its atmosphere. But a groundbreaking new study using NASA's James Webb Space Telescope says otherwise. By capturing SIMP 0136 infrared emissions across 2 full rotations, Webb peered beneath the surface, revealing a rich, layered atmosphere where clouds alone don't tell the whole story. What scientists discovered were intricate changes in cloud structure, shifts in temperature, and even evolving patterns of carbon-based molecules. In other words, SIMP 0136's atmosphere is a dynamic, ever-changing system, not unlike the gas giants of our own solar system, but even more complex. This kind of deep atmospheric analysis is exactly what researchers need to prepare for the next great leap, directly imaging exoplanets using NASA's upcoming Nancy Grace Roman Space Telescope, set to launch in 2027. Understanding rogue objects like SIMP 0136 helps us fine-tune the instruments and methods that will soon be used to search for new worlds orbiting distant stars. And while SIMP 0136 may not be bound to a star, it's uniquely suited for study. Free from the glare of a host sun and blazing brighter than any other object of its kind when viewed from the north, it offers an unfiltered window into alien weather systems. It's also been a favorite of astronomers for years, observed in the past by ground-based observatories, as well as NASA's Spitzer and Hubble space telescopes. But with Webb's powerful near-infrared eyes, we're finally beginning to peel back the layers and glimpse the alien skies of a planet without a home. This is just one piece of the puzzle in a much bigger cosmic picture. It's a lonely wanderer, SIMP 0136, an isolated planetary mass object freely drifting through the galaxy. And now, thanks to the James Webb Space Telescope, we're learning more than ever before about the strange and changing weather on this mysterious world. Allison McCarthy, a doctoral researcher at Boston University and the lead author of the study, explains, "We already knew that SIMP 0136 varied in brightness, and we're confident that patchy cloud layers rotating in and out of view evolve over time. But we weren't sure what else might be behind these changes. We suspected temperature shifts, chemical reactions, even auroral activity could play a role. To investigate those possibilities, scientists turned to Webb's extraordinary ability to detect ultra-fine fluctuations in brightness across a vast range of wavelengths. Using the telescope's powerful NIRSpec and MIRI instruments, they closely monitored SIMP 0136 as it spun twice in just 2.4 hours. Across those rotations, they tracked how different wavelengths of infrared light changed, a method that revealed more than just surface clouds. They found distinct differences in cloud cover at multiple depths, temperature variations in the upper atmosphere, and even evidence of dynamic changes in carbon chemistry rotating in and out of view with the object's spin. Although Webb didn't capture a clear image of SIMP 0136 itself, its spectroscopic capabilities painted a vivid picture. To visualize the findings, artists created a concept image, a representation of what SIMP 0136 might look like based on Webb's data and earlier observations from Hubble, Spitzer, and ground-based telescopes. This is more than just a study of an exotic world. It's a proof of concept, a demonstration of how we can probe alien atmospheres light years away, layer by layer, without ever seeing them directly. To uncover the secrets of this mysterious, drifting object, SIMP 0136, NASA's James Webb Space Telescope used one of its most powerful tools, the Near-Infrared Spectrograph, or NIRSpec. For nearly 3 hours, as the object completed one full rotation, Webb recorded an astonishing sequence, collecting thousands of individual spectra at wavelengths ranging from 0.6 to 5.3 microns. Each reading captured every 1.8 seconds. That's nearly one new spectrum every heartbeat. Then came the next phase, a follow-up observation using Webb's mid-infrared instrument, or MIRI. This time, the telescope gathered light readings between 5 and 14 microns. Hundreds of mid-infrared snapshots were captured every 19.5 seconds over the course of another full rotation. As SIMP 36 spun, the results came to life, a tangle of intricate light curves. Each wavelength, or color of light, pulsed with its own unique rhythm, revealing how brightness changed as different parts of the object rotated into view. Dr. Joanna Voss, a leading scientist from Trinity College Dublin, put it best. It was incredible to see the full spectrum of this object change over the course of minutes. Until now, astronomers relied on limited data, narrow near-infrared spectra from Hubble, and coarse brightness measurements from Spitzer. But this was a new frontier. And the surprises didn't stop there. The team quickly noticed that certain wavelengths were growing steadily brighter. Others were dimming, and some barely moved at all. Each pattern told a story of clouds swirling at different depths, of temperature gradients layered through the atmosphere, and of molecules shifting, breaking, and reforming in real time. To put it in perspective, imagine looking at Earth from light years away. You might not see mountains or forests, but if you could study the light, color by color, you'd start to decode the planet. As co-author Philip Muirhead from Boston University explained, even if you couldn't make out individual features, analyzing each color separately would reveal patterns that tell you something about the surface and atmosphere. The blue would brighten as oceans rotated into view. Shifts in green and brown would hint at vegetation and soil. That's what Webb did for SIMP 0136, watching its alien weather unfold one wavelength at a time. What happens when you watch a wandering world for hours through the eyes of the most powerful space telescope ever built? You get light curves. Thousands of them. This is SIMP 0136, a free-floating planetary mass object. It's not tethered to a star, and it's about 13 times the mass of Jupiter. On July 23, 2023, the James Webb Space Telescope turned its near-infrared spectrograph, or NIRSPEC, toward this object for a full 3 hours. In that time, it collected an astonishing 5,726 spectra, one every 1.8 seconds, capturing the light at 3 different near-infrared wavelengths as the object rotated through space. The result? Oscillating patterns of brightness, a signature of complex and layered atmospheric activity. These light curves tell a story of clouds, but not just any clouds. We're talking about deep, dense layers of iron particle clouds, high-altitude wisps of silicate dust, and fluctuating hot and cold regions in the upper atmosphere. Each of these elements comes in and out of view as SIMP 0136 spins just once every 2.4 hours. To make sense of it all, researchers model the atmosphere in layers, like peeling back the skin of an onion using light. Thicker arrows in the model represent more intense light emissions. Thinner arrows mean dimmer regions. Each arrow is color-coded to match the light curves, showing how different parts of the spectrum probe different atmospheric depths. Alison McCarthy, the study's lead author, explains, different wavelengths provide information about different depths in the atmosphere. It became clear that the wavelengths with the most similar light curve shapes were probing the same depths, which suggests the same processes are at work. One group of wavelengths points to patchy iron-rich clouds deeper down. Another probes higher-altitude clouds made of silicate grains, creating separate, distinct curves of light and shadow. But a third wavelength behaves differently. It traces temperature changes, possibly tied to upwelling columns of hot gas. Or even auroras, bright atmospheric displays similar to Earth's northern lights, but far more powerful. And then there's something even stranger. Some of the light variations don't match any known cloud or temperature pattern. Instead, they seem to reflect changes in atmospheric chemistry, likely driven by swirling pockets of carbon dioxide, carbon monoxide, or methane, or by chemical reactions taking place as the planet rotates. Dr. Voss, one of the co-authors, puts it simply, we still don't have a good grasp on the chemical component. But these results are exciting. They suggest that chemical abundances, like carbon dioxide and methane, might vary both across the surface and over time, which means a single snapshot of an exoplanet may not tell the whole story. This study was part of Webb's General Observer Program 3548, and it's redefining how we think about alien weather and atmospheric evolution. SIMP 0136 may be alone in space, but it's not silent. If you enjoyed this journey through space and time, don't forget to like, subscribe, and ring the notification bell so you never miss the next voyage with Spaceverse.